Welcome back. Um, I believe this is where I left off. I lost the original file. I lost the original file, so I had to attempt to recreate it from the original video. So here we were in a suborbital trajectory up to 200 kilometers, and as the lady so kindly reminded us, our APU fuel is still going down. And the APU stands for Auxiliary Power Unit, and it has a limited amount of fuel. It's visible right here, and it powers everything that moves by hydraulics. So that's the AF control surfaces, all of the doors that move like a radiator. So if nothing is moving, you're just wasting fuel by having it running. So keep that in mind. APU fuel is right here. It is very limited, and you cannot get more until you find somewhere that has fuel. So RCS, I told you what it is, but it stands for Reaction Control Surfaces, and I believe almost everything that goes into space has them. The International Space Station, I think, has them, just slightly differently because it's not as compact and awesome as the Ravenstar or the Space Shuttle. It's kind of all gangly and large. So it might just have reaction control surfaces of like the Soyuz that dock with it, but I'm not sure. So that's that. So I'm gonna speed up till we get closer to apogee, and hit this button right here, which is prograde, which means that it'll orient our craft directly forward in the orbit, which under the... So this is the heads-up display we used for takeoff. The orbit heads-up display is useful because it shows you orbital information, whereas the surface takes into account how the Earth spins. This is just in relation to the center of the Earth, which, while spinning, doesn't really matter because it's a point. So the apogee is, like I mentioned, it's the highest point in the orbit, so it's where you start. It's where you go from, going up, and then once you hit the point, you start going back down, which is visible here in our vertical speed. It's in the negatives, which is why I have positioned my nose above the prograde, so I can get it back up to the positives. And my goal is to get both the vertical speed and the vertical acceleration as close to 0 as possible. And as you go faster, your orbit rounds out, so you need your nose to be closer and closer to prograde. And eventually, when it gets perfectly circular, I will be pointed directly at prograde. So it just takes a little bit of fine-tuning, and don't worry if you don't get it exactly correct, because, I mean, at 200 kilometers, we're high enough above the atmosphere. Technically, I mean, there's still air, but we're high enough that it doesn't, like, we could stay here for a while and not get dragged down. So there we go. You just saw something happen over here, and that was this little red thing. AP is the apogee, and you may have seen it flash by, but right now it's directly underneath our altimeter is the PE, which is the lowest point in an orbit. So we have a variation in orbit of about 2 kilometers, which is very, very good. So I'll just keep it there. So that's that. We have our orbit. It's nice and stable for a few days at least. Well, more than a few days. It'll take a while to degrade. So next we need to align our planes with the International Space Station. So you can do that with the Align Planes MFD. So I'll target the International Space Station. You can also target by name. So I type in ISS, and it'll do the same thing. I mean, nothing changed because I had already targeted. But if I targeted, say, Mir, already yelling at me. So if I target mirror and then type in the ISS, it will target the ISS, and now it's confused. I don't want it to be confused. Hang on. Dang it. Let's try to get off of that. There we go. So this little information shows you a little bit about our respective orbits, and that gets more understandable when you compare it. I guess like you'll use the map. When you compare our orbits like this, I'm gonna do orbit plane. So as you can see, this green line right here is my orbit. The yellow line is the International Space Station. And as you can see, they're not lined up. And that's a problem because even if we're at the same altitude and the same period as the International Space Station, we could be hundreds of kilometers apart because we're just orbiting in the different planes. So that's what this tells you. These lines right here are where our orbits cross. So you can see right here over Cape Canaveral, and the next one happens over here in the... Is that technically the Indian Ocean or the South Pacific? West of Australia. AN means ascending node, which is the node at which you are ascending the Earth. DN is the descending node, which is the node that happens when you're descending the Earth. So that's what AN and DN are. When I was originally learning how to do this, I thought of them as antinode and DN, which I just called delenode for some reason. And the reason I called it antinode was because at AN you want to be orbit antinormal, which is done by this negative sign. And as you can see, the negative sign corresponds to these negative degrees in the orbit heads-up display, which is why orbit is very useful. And DN corresponds to just normal, which I just remember that because it's not antinormal. So that's what I do. Officially it's ascending node and descending node. So there's that, and what this does is it points me at a perfect 90-degree angle from prograde. So if I fire my engines right now, it wouldn't affect the speed or apogee or perigee, and I know it's not perigee. Sorry, I'm mispronouncing it. I just always call it perigee, PEG. It won't affect any of those, but it will affect the plane of the orbit. And that happens, so right now I'm at the antinode, or antinormal, and I want to fire my engines when I get to the antinode. So I'm going to speed up, passing into the night side. Down here, the est thrust T, which is estimated thrust time. Oh, actually, we're about to have sunset. Yay, sunset. At estimated thrust time is how long this MFD expects you to fire your engines to correct this relative inclination of 6.14 degrees. And this TN is time till the node, which is how long until you get to this node. And so, logically, we should start firing, or we should fire half of our thrusters before the node and half of the thrusters after the node, which means that we will start firing at about 24 seconds, when Tn equals 24 seconds, and we have just passed in the night side, and I'm sorry I missed it. We'll see plenty of nights and days here. So anyway, that's what I'm waiting for, is about 24 seconds. So I'm going to reactivate the normal. And this button will actually start flashing when it tells you to engage thrust, orbit normal. So it tells you even what, or orbit anti-normal. So it tells you what direction to take and when to start firing. One thing you'll notice is that my ship is glowing because of the engines, and I'll talk more about that after I've got time. And what this is I have activated in Orbiter the module that allows for localized lighting, so my engines will light up the spacecraft at night, which is very, very cool and handy. And not every add-on vehicle will do this. The space shuttle that comes with the default orbiter, I think, does it, but very, very few others do it. So I'm happy to see that the Ravenstar does it, because it's a very cool effect. So there we go. Now our relative inclination is 0.01 degrees, and you can see here that our orbit planes are so close together that it makes no odds. I mean, you can't even see the yellow one anymore. And I know I said this was going to be 2 parts, but I'm worried about this session running overtime, so I'm going to stop it here and do the docking in the next video or the video after that. So hopefully this works.